All right, let's resume our discussion. So this is the second part of our discussion on counterfactuals, and we're going to do three things in this second part. First, we will talk about structured causal models, which is the more standard input used for counterfactual reasoning today as opposed to functional Bayesian networks. And then we're going to talk about the syntax and semantics of counterfactual queries now more generally. And that's going to be a fun discussion. We're going to see how simple and nice you can formulate this and then go beyond the prototypical queries. You can have an open-ended kind of counterfactual queries. And then the last part would be identifiability. How can we do this in a practical setting? How can we do counterfactual reasoning without having a complete model like what we've done. Now, but to start, I want to stress again this notion of an information hierarchy because, again, as I said, it's not stressed enough. Parallel to the reasoning hierarchy, associational, interventional, counterfactual, there is what kind of information you need for each. Bayesian network, causal Bayesian network, functional. Once more, here, all I need from the graph is to have the right independence assumption, and therefore it induces the right distribution. Here, I want, no, it's not enough for the causal or for the structure to display the right independence information. It has to be causal. And in a functional Bayesian network, I want the internal nodes to be functions of their parents. Now, and once more, let me stress, you do not need this for interventional reasoning. This kind of additional detailed information is not needed for these guys. But the other thing is, as I said earlier, people talk about structural causal model instead of functional Bayesian network. And once more, these more generally are broader than these guys, but given how people use them today, they're pretty much the same. So let's talk about structural causal models, pretty simple. As you'll see, I'm going to be using a running example in the next few slides. And this example comes from this paper on Pearl's hierarchy and the foundations of causal inference by Berenboim and colleagues. It's an excellent paper, by the way. It was written for a special book that was prepared for Yuda's work. We'll give you a pointer for this in the video. Now, we're talking about this kind of a causal structure. We have these 4 background variables and 3 internal variables. And if you want to specify this fully, you need distributions over the background variables, and you need equations for these guys, right? So in this case, we're assuming all of these are binary, and so it's sufficient to give you these numbers that specifies these guys. Now, for these guys, instead of giving you these functional CPTs, we usually write equations that happen. That's what happens in a structural causal model. So in this case, here are the equations. Okay, this looks a bit hairy, but it's more innocent than it looks. And let's look at X. X is a function of this variable and that variable. And this is what's saying the function for X. These are the inputs, and this is the specification of the function. X would be true if Z is true and this guy is true, or Z is false and that guy is false. That's it, right? Let's look at Z. Z is a function of these 2 things. And I'm saying it's true if this is true and that's true. I need both. So it's like an AND gate in this case. Now, realize what happened here is these are binary. In principle, these could have had a lot more values. So I'm kind of assuming the other values are impossible. That's what is structural causal model, right? It's functional Bayesian network in this case. Distributions of the roots and equations for the other guys. Now, the standard terminology is for these background variables is we call them exogenous variables. So these are the guys, okay? And these guys here that have these equations are called endogenous variables. So here you go. That's what is a structural causal model. Now, the assumption is that the exogenous variables are hidden. So when you get to the practical setting, you get only observations over these guys, but not over those guys, okay? that's basically what a structural causal model is. Now, I need one more notion before we go into the syntax and semantic of counterfactual queries, which will be defined on structural causal model. Now, this is a wrap up of our discussion on intervention, but it allows me to give you what the term submodel. That's what people use to the model that results from removing parents of a node. So what happens here is I have this model and I'm gonna say, let's intervene to set the value of X to this value. So I wanna do. And in this setup, what people say, okay, you do your computation on a submodel that results from removing these guys. So that's the new structure, right? That's what we talked about last time. Now X is not driven by these guys because I'm going there and fixing its value. And what people also describe this intervention operation is by saying, okay, you had an equation for this guy. You now have to take it out. It was this equation that was showing its value in terms of the two parents. Now take it out and replace it by that. So you will see this picture where you have the equations and then one of the equations is removed and replaced by another. It's just exactly what we did before, right? But this is the notation and language used in this context. And we call this a submodel, look notation. This is M sub X, right? The submodel I got by setting the value of X to that particular value. I hope this is very clear. Now, we're going to use this notation when we talk about syntax and semantics. So structured causal models, the notion of a submodel. Let's now go ahead and talk about the syntax and semantics. And I have to tell you, what you're going to see next is a little bit more general than what people tend to do, and you'll see the purpose for that, but it's very simple. Essential to understanding the semantics of counterfactual is this notion of a world. Please pay attention to this slide because it's going to give you a major insight about how these things work. What is a world? It's a little bit of a generalization of the notion of a world that we talked about before. Same concept. And by the way, the next few definitions are coming from this paper. We'll give you a reference. It's a very recent paper, a couple of months ago. A world is an instantiation of the exogenous variables, the roots. Now, why? Why didn't we include all variables? Usually when we define the notion of a world, it's usually an instantiation of all variables. Because in a structural causal model, and because the endogenous variables are functions of their parents, the minute you fix the value of the exogenous variables, these guys get fixed as well, right? Let's see it. I have 4 variables here, exogenous. So they're all binary. Then there are 16 possible instantiations. Now, every time you pick one of these, there's 0, 0, 0, 0. The values of X, Y, and Z are determined by the equations, right? So I can now add them, they're implied. The states of endogenous variables are fixed in a world, and here they are. You can check them. Take this guy, use the equations for X, Y, and Z, you're gonna conclude these values. Pick this guy, you're gonna conclude that value and so on, all right? You have to imagine this. It's very important that you fix the roots and then everything is fixed, no uncertainty. The other thing you need to know is the probability of a world. Now, these are roots. What does that mean? They are independent. So if you pick any combination, let's put word 6, this is 0, this is 1, this is 0, this is 1. What's the probability of that? Well, you just have to take the probability of this guy multiplied by the probability of that, by the probability of this, by the probability of that, because they're independent, they're roots. So using the 4 numbers I gave you that shows the probabilities of these 4, you can go and show the probability of every one. All right? Key observations. The notion of a world is a fixation of the exogenous variables that immediately implies values for the endogenous variables. The probability of a world is pretty easy in this case, just the product of all probabilities for the integers. Now, sometimes people will tell you, oh, I don't want to assume these guys are roots, Yes, you'd see that, but not a lot of results are developed. What I'm showing you here is what mostly used in practice. Now we get to the very key notion that gets us to the semantics. What we're up to, and we're going to do this in almost 3 slides, is I want to be able to take this guy and show you how to systematically compute the probability of something like this, okay? Given that X is false and Y is false, what is the probability that if I set X to true, Y will be true? And further, if I were to set X to false, Y would be false. Now, this is just that, right? So the probability of this divided by that. So I want to be able to show you how do you compute the probabilities of statements like this, which we have not seen before. We're going to call these events counterfactual events. Why they're counterfactual? Because look, here's X is false and here's X is true. So they look apparently clash. And you're going to see this. And then you can do even something more complicated like this, right? What are you saying here? Given that now X is false, and given I'm in a situation where Y is false, and given that I'm in a situation in which if I were to set Z to this value to true, then Y would be true. Given all of that, what is the probability that if I were to set X to true, Y would be true? And further, if I were to set X to false, Y would be false. That's this. So again, if I show you how to compute the probability of this guy, we're done. And you see how easy it is in just a little bit. It's all gonna revolve around the notion of when does a world satisfy an event like this guy? When is this true in a world? I pick a world, we've seen 16 of them. I pick one of them, and then I pick this statement, and I say, is this true in that world? If I show you how to do that, we're done. Why? Because to compute the probability of an event, I simply look at all worlds that makes it true, in which it holds, and I add up their probabilities. You've seen this equation, chapter 3, I believe. Same story. The only thing is this guy. And you'll see now it's straightforward. And then you have a mechanistic way to compute the probability of any query. Now, if you want to do it efficiently, then you have to go to twin networks or invent your own. But we have to at least establish what is the correct answer. Because if you come to me and say, oh, I know how to do it, I'm going to use a variation of the twin network called this and that. Well, what I'm going to show you in the next 2 slides first would be the guide for you if you're doing it right or wrong, because this will give you the equation of what the right answer is. Okay, guys, let's do it. Now, before I show you the notion of satisfaction, I just want to more formally define these creatures. So there's 2 slides really. The slide that show you what these guys are, what their syntax, because they're simple, and then the slide about defining this. And we'll take concrete examples. You see this in action. I'm going to define the notion of an event. And I'm going to make a distinction between observational event, intervention events, and counterfactual. Okay, this looks too complicated. It's not. First of all, you know what observational events are. This is what we've been doing in the class so far until last lecture. That is, you have some variables and they get some value. That's an event. Variables X took that particular value. We're going to call this observation event. And remember, endogenous variables. We don't observe exogenous ones. So examples, list, X is true. Another event, Y is false, Z is true. X is true, Y is false, Z is false, and W is true. These are 3 different observational events. We've spent, what, 3/4 of the course just working with the observational events. Okay, interventional events, you've seen them, except we're doing a little more general now. This is an interventional event, it has this form. And what does this mean? That means these variables will take this value after setting X to this value. That's it. Now, you've seen it so far where Y and X were individual variables. They don't have to be. These could be sets of variables. So let's look at some concrete examples. Y is true if I set X to true. Now, what happened here? Y is true if I set X to false and Z to true. Now, here it is more. X is true and Y is false after I set Z to true and set W to true. Okay, this is legitimate. These are interventional events. Now, what is the last type, the counterfactual? Just take a bunch of these and paste them together. Pick any combination of interventional and observational event and put them together in an and. That's a counterfactual. That's it. So it's this, where this guy is either observational or interventional. Now, what does that mean? That means this and this and this and this and that. Let's look at concrete examples. So what happened here? This is observational event, or you can look at the whole thing as an observational event and an interventional event. And I put them together. I said this and this and this. So I'm telling you, X is false, Y is false, and Y would be true if I were to set X to true. That's a counterfactual event. Let's look at this guy. What is this? Two interventional events. And I'm saying this intervention and that. If I set X to true, Y is true. If I set X to false, Y is false. Okay, let's look at this more involved one. What happens here? We have three interventional events, this, and that, and we have an observational one, and we just put them at that, and that. Okay? If I set X to true, Y is true. If I set X to false, Y is false. Z is false. If I set Y to true, Z would be true. I hope this is clear. Pretty simple, but at least now we have formally defined the notion of an event being observational, interventional, or counterfactual. Now, what do you call counterfactual? Because the possible conflicts, right? Now, here you can have conflicts. I can put here, I can add X false, but then it would be a trivial event. It would be a false event, no inference, probability is 0. Now here, you can have conflicts. Like here, this is false, and here you're talking about setting it to true, but this is not a trivial event. This is a meaningful thing that will not give you probability 0, right? So the notion of counterfactual is this conflict that apparent that may appear between these guys, but no, they're not going to give you 0 properties. Okay, so now we're ready to talk about when is it that you give me a world and you say, you pick any of these guys, whether observational, interventional, or counterfactual, and you say, is it true in that world? Will the world make this true? Will this hold in a particular world? Now, of course, this is a generalization. If you have this, you don't need these guys. They're just conceptual. This encompasses both this and that. Now we're going to show it, and you're going to see how straightforward it is to define satisfaction. All right, here it is. And then we'll take a concrete example. The first part, which is observational events, is straightforward. We already did it. This is chapter 3, right? We're defining this relation now, whether a particular event holds in a particular world, and everything is, with, of course, with respect to a particular structural causal model. That's the first guy. You know this. What did we say about worlds? When a world fixes the value of exogenous variables. Now, the minute you fix the value of exogenous variables, the values of endogenous ones are all fixed. So if you want to say if this holds, just go and see what are the values for X in this world. Do they match? Then yes. Straightforward. Right? So this is whole if world who fixes endogenous variables X to X in STM. That's straightforward. Again, we'll see a concrete example. Now, the last one for counterfactual will be straightforward. The interesting one is what's coming next for interventional ones. Pay attention to this. It's very brief but subtle. What am I doing here? I'm giving you this. I'm saying I set X to this value and then Y take that value. Does this hold in this world? Now look what I'm going to do. I'm going to transform it to a question of this type. But instead of using this model, I'm going to use this submodel. I'm going to say, okay, I actually have to do this. Very easy. Take this model, mutilate it to set the values of X to this. That is, remove the parent. Okay, now I have a new submodel, new structural causal model. Okay, and in that one, ask, is this observational event true? Right? Just like here, if I set the value of U, the background variables or exogenous variables, every endogenous variable is determined. The same is true here. So I just do that. And again, we'll see a concrete example of that. Now, what about the last case? Straightforward. Does this hold in this guy? Well, just check. Each one of them must hold. If this holds and if each one of these guys hold, then yes, the conjunction. Remember, comma you want to think of it as and. All right, that's it, straightforward. Let's do a concrete example, okay? And we're going to use this running example from earlier. 4 exogenous variables, 3 endogenous, right? Remember, 16 possible worlds, and here they are. And now the question is, I want to know this observational event. X is false and Y is false. Which worlds satisfy this? Okay, now this is straightforward. This is saying 4, 8, 11, and 13. Now why? Because all you have to do in this case is look up the worlds in which X is false and Y is false. That's it. There's 4 of them. Here. False, false. Or 0, 0, 0, 0, 0, 0, 0. That's the only one. That's straightforward. That's actually what we've been doing also far with associational reasoning, right? So if I want to compute the probability of that guy, I just add up these 4 numbers, right? Okay, but now let's do the other one, which is the more interesting. I want to show you an example of interventional event. This. Which worlds make this true? Or in which worlds does this hold? That if I set X to true, Y will be true. All right. Now, to do this, you have to operate using this guy. So again, you have to establish, you look at the 16 possible worlds and you compute the values of X and Y and Z in each one of them, but using this guy now. What's the difference? This is no longer following these 2 guys. This is fixed to 1 in this case. So you're not going to compute this based on those. You're going to always fix it to 1. And now when you compute the value of Y, it's going to be always with respect to X being 1. Now we can do this by modifying the previous table. This was the previous table. Look what we're going to do. We're going to go to X, because in the previous table, X was being computed based on these 2 guys. So sometimes it's 1, sometimes it's 0. Now we're going to go to the places where it's 0, force them to be 1. These are the ones, okay? Now, when we do that, we have to adjust the value of Y, because now Y is being computed based on X being 1. Now, Y had this equation. If you fix X to 1, it simplifies to that. What does that say? Now, Y have to follow this guy. So now that this is 1, we'll just take the value of this guy. So we have to adjust the values of Y. So what happens? In this whole table, this guy is always 0. So Y should always be 0. Here it is not, here it's not. I'm going to fix that. So in all of this part, this variable is always 1. So Y has to take the value 1. So I'm going to fix these guys. Okay. Now I have the right table. I hope you see what happened here, right? I have the exact same set of 16 worlds, except the values X, Y, and Z now are determined differently. Why? This is always 1. I fixed it. And Y has to be computed with X being 1, and that's the table. Now, if you look in these, you're going to find in these 8 here, Y is always 1, which is what I want. And in all of these, it's 0. So the interventional event, this one, is satisfied by these worlds. Okay, now look what happens. You're ready. Look how beautiful this is. What we did is I showed you that for this observational event, the worlds that makes it true or in which it holds are these 4. And then I told you the interventional event, this guy is true in these worlds. Now I'm interested in those worlds in which both are true. So I'm looking now at a counterfactual event, which is this, and that. That is, the event is X is false, Y is false, and if I set X to true, Y will become true. What is those worlds? Just the intersection of these guys. So it will be 11 and 3, because I have this and I have that. This counterfactual event is satisfied in these 2 worlds, because those are the only ones that satisfy both this and that. What are we ready to do now? We're ready to do this. We're ready to compute the probability that if I set X to true, Y will become true, given that X and Y are currently both false, which is just this divided by that. I know what is the probability of that. Just look at the worlds that satisfy this and add up their probabilities, 2 of them. What about this guy? 4 worlds satisfy this, add up their probabilities. I have those, I got this problem. Straightforward. You just need to know the notion of an event and what worlds it's satisfied at, and then the rest is straightforward. All right. Now that I have this, now I can freely start writing equations and do all kind of things. What does that mean? I can now talk about independence between two counterfactual events or two interventional events. I can go and tell you, is this independent of that? Now we're ready to go and phrase these two properties more formally, because now we have the language. We did it intuitively before, right? Start with X is exogenous relative to Y. Don't read these two guys yet. The intention is I want to be able to kind of reduce action to observation. Here's the condition. This event is independent of that. And this event is independent of that. What does that mean? We can write it now. Say, probability of this given that is the same as that. Probability of this given that is the same as that. This is meaningful. This is one of the conditions people use to basically state results in practice. And we're going to see examples of those later. The essence of this is it allows you to replace interventions by observations. And by the way, there are two versions of this notion of X is exogenous relative to Y. If you look in the Causality book, you find in the actual book there was a stronger version. And it was the very end of the book that added some pages based on latest results that use this weaker version. So there is strong and weak versions of this, and this is the weaker version. The other one is monotonicity. That's simpler to state. And earlier I gave you an intuition behind it. Y is monotonic relative to X if the following is impossible. Right? That, what does this say? That if you set X to true, Y becomes false. But if you set X to false, Y becomes true. This event is unsatisfiable. No world satisfies that. Now, we looked at this in a very localized case earlier where X was a parent, and we saw that means if you look at the CPT, one of the rows must be 0. But this is more general. This does not require X and Y to be parent and child. So you can pick any nodes in the model, in the structured causal model, and this says you cannot have this. And actually, this is how it's stated in Yu's book. That's too restrictive. What you really want is this. This is more general because this could be satisfiable, but its probability is 0. Right, so it's just you don't want that kind of a relation between X and Y. That's impossible to have that kind of a relation between X and Y. All right, okay, guys. So we're almost ready now to go and show you examples of identifiability results. They're going to be easier than what we did for causal effect. You'll see why, because they're simple equations and bounds. But I just want to do two more quick things before we get to that final part. And first, I want to show you that what we did here is a little bit more general than what people typically do. And because of the way that we did it, you can now have open-ended kind of counterfactual queries. Most of the literature is focused on prototypical ones, probability of necessity, sufficiency, probability of necessity and sufficiency, but you don't have to. For counterfactual events, we did this. We assumed that you have a conjunction, and we said, is this conjunction true in the world? Right? We put commas, right? But it's the same as conjunctions. And they said, yeah, it's just, this has to be true, this has to be true. Well, you can do this too, right? You can say or. You can say, is this true in this world, either this or this or that? And you say, yeah, that's if and only if this is holds or this holds. And you can do negations, right? You can go and say not eta. Well, straightforward way. Now, when you do this, now you can talk about the truth of any Boolean combination of observational and interventional ones, right? So now you can do stuff like this. Assess whether a patient is a responder given the arithmetic contrarian. What am I conditioning on here? This means a contrarian. If X is true, Y is false. If X is false, Y is true. No, it's not a contrarian. What does that mean? It's one of the other three. Given that it's not a contrarian, what is the probability that it's a responder? right? You can do this. This is meaningful. You can do something like this. Assess whether a patient would not have developed some symptom had they been on diet or alternatively had they exercised. So what's going on here? Someone didn't exercise and they did not diet and they developed a symptom. And I'm saying, given that, what is the probability that they will not have the symptom if they were to exercise, to diet, or they would not have the symptom if they were to exercise? We're able to do this because we use this notation here. And typically people don't do that. People typically use this notation. And they would write this to say X took the value this in that world. And in this world, if I were to intervene and set X to this, then Y will take that value. If we want to say these things in this notation, we would write this. This is true in this world. This is true in that world. And it becomes easier to write statements like this. So what is this saying? In this world, I have this and that. What is this? X is true, or Y would be true if I said X is true, and not this. This world, it's not the case that if I set Y to true, then Z becomes true. If I set Y to false, Z becomes true. It would be cumbersome to write it using this guy. Okay, let's get to the last part now about identifiability, which is the practical setting. And this is going to be a quick discussion, and you see why. You'll see two kind of identifiability results. One of them will just say, here's the causal effect you're interested in, and here's the exact point estimate. And they require conditions. The other more popular is bounds. We don't give you point estimates, but we bound the counterfactual queries. So what you're going to see next is a sample of either point estimates or bounds. But the thing I want to tell you to pay attention to as we move on is two things. What are the conditions that are assumed for those to hold? Second, identifiability now is using what kind of data? When we did intervention, the data was observational. And the question was, can I get or would I be able to compute an intervention query using observational data? Now, we want one level up in the causal ladder. So we're talking about counterfactual queries. So it's now relevant to ask, not only can I get it from observational, but can I get it also from interventional? Observational data people usually call non-experimental, and interventional data is what we will call experimental data. So what you're going to see next is sample. Some of the things I'm going to show you, you can compute counterfactual queries using only observational events, and some using only interventional. And the fancier ones use combined. They can use a combination of observational and experimental. All right, so they're easy, as you'll see now. We'll just state them. I'll just give you either identities or bounds. We'll start with this one. This says, if X is exogenous relative to Y and Y is monotonic relative to X, then the probability of necessity and sufficiency is just that. In fact, two conditional probabilities, Y given X, Y given not X. Let's just look at this carefully. Exogenous relative to Y, you can establish that given the causal structure, because you have to assume that you have a certain causal structure. So monotonic people typically assume it. They say, well, in this situation, I'm going to assume monotonicity. That means I don't have contrarians, and then you trigger this. This is using observational data, because these quantities you can get from observational data. So this is an example of an actual point estimate based on observational data and under these two particular conditions. Okay, now I'm going to show you a version of this which would not require this. And let's look at it. It will only require monotonicity. It's very similar, but instead of conditional probabilities, I have interventional probabilities. But in order for you to do this, these have to be identifiable. Now, we talked about identifiability of interventional probabilities or causal effects last time. So remember, everything we're doing here in the background, you sat and drew a causal structure, said, this is my causal structure. and this is my data. So you take your causal structure, your data, go back to what we did last time, and maybe you can establish that this is identifiable, this is identifiable, done. So in this case, you all have to assume is monotonicity. If you believe your scenario, the assumption of monotonicity is reasonable, you can invoke this and you can do that. Okay, we're still observation. So we just weakened the condition a little bit, but we're still in the world of observation. Here's another result. Now, this is a bound. So far we had equalities, and now from now on, we're gonna look at bound. And by the way, everything here we're doing is PNS, probability of necessity and sufficiency. There are parallel results for probability of necessity and probability of sufficiency. We're not doing that because this is exemplary. And again, you can consult standard references and you see the full slew of things. This bound is as follows. Now, let's look again. We need to pay attention to two things. One is, what are the conditions? Second, are we talking about observational or interventional data? We're still in the world of observational data. And we only need X to be exogenous relative to Y. And here's the bound. It says this is bounded from below by this, bounded from above by that. Look what happened here. Conditional probability, conditional probability, conditional probability, conditional probability. All this can be estimated from observational data. A version of this that does not require this, but needs interventional data is this guy. It's pretty much the same, except that instead of the conditional probabilities, I have interventional ones. See, this condition is so that these equate. Now, this basically says I need these guys. Now, you can get them from interventional data, or alternatively, if they were identifiable, they're also good, right? And then you can have these bounds. I just want to show you two more things, two more bounds, more sophisticated than anything we've looked at, but they're also more detailed. Those bounds, they will get into the business of having both interventional and associational. Everything we looked at so far either had associational quantities, and therefore you could estimate them from observational data, or had interventional ones, and you can get them from interventional data or from observational data if they were identifiable. The next two ones we're going to see combine observational and interventional quantities, and therefore can be estimated or applied when you have that kind of data. And the very last slide, or one before last, I'm going to show an example of combined data, but let's do them. They're both more detailed, and this is the first one. So we are bounding the probability of necessity and sufficiency, and it's saying this and that. So it's greater than or equal to this. You have 4 quantities, take their max. You have 4 quantities, take their min. The key thing you have to realize is we have both interventional and associational. So interventional. This is associational. All of these are associational. No, just these two. These two. All right. So in principle, you need interventional data to get these guys and observational data to get that. The last bound we're going to look at is actually very, very recent. This is our own TA, Scott Muller. We just had this recent result. Before I show you the result, it's very similar to this guy, except that it uses a very interesting observation. Look, this guy does not invoke anything about the structure that you have. And the next bound that I'm going to show you is like, okay, if you have some variable z, and those variables do not contain any descendant of x, x is the guy we are intervening on, then I can use them and do case analysis on them to improve this bound. So what you're going to see next is you're going to see here a summation over possible values of z, and similarly a summation here over possible values of z. There's interesting intuitions of what's happening there behind that case analysis. We're not going to talk about it here. We're almost done, but we have the real expert, Scott. So here's how it looks. It says if z is a set of variables that this set does not contain the descendant of x, then you have this. Now this is just exactly the previous one, but I'm summing over possible values of z here and there. And look what happened. Every quantity now become conditioned on z. Okay, compared to this. It's exactly this guy, except that condition on z, and now this is what you're getting. And this would give you tighter bounds than before. Let me just also emphasize, now we're also doing experimental and non-experimental data. No assumptions made. Okay, I mean, is this an assumption? Yes, we're just assuming that that Z do not contain any descendants. Really, really very weak. This is a passage from the Causality book about this combined data. And then I'll show you an example, very simple example of combined data before we end. In drug-related litigation, where people, this is where the person would be alive but for the drug. So if someone took the drug, they died, would they be alive if they did not take the drug? We're trying to compute the probability of necessity and such. In drug-related litigation, it's not uncommon to obtain data from both experimental and observational studies. The formal is usually available at the manufacturer or agency that approved the drug for distribution. That's the standard procedure for basically approving drugs. You do experiments, right? You get people, have control groups, say, take the drug, take the placebo, okay. While the latter is easy to obtain by random surveys of the population, all right? So very simple example of combined data, and this is from Yuda's book. In chapter 9, where he talks about these bounds, there's some nice scenarios towards the end where he does evaluate some of these counterfactual queries, but here's what the table looks like. So I'm talking about two variables here. X, which is drug, took the drug, did not take the drug, and Y, death, survival. And you see two types of counts, observational and experimental. This is what manufacturer will do when they're doing control experiments. 16 took it and died, 984 took it but survived. Now, this is observational. This is no controlled experiment. Someone went there and just looked at people and collected numbers. There's that many that took the drug and died, that many did not take it and died, and so on. Now, when you have this, then you can go and do two types of estimates, right? So you can estimate this. These numbers here are obtained from this table. And these are observational. They're obtained from that table, right? And then you can start plugging these quantities in these equations. Now, of course, there is the issue of coherence. They have to match in some way. So we're not talking about this here, because you may give me experimental and observational data that do not match in a certain way. All right, so we're done. We're done here. I just want to have a couple of concluding remarks on our discussion. The causal hierarchy, it really has two dimensions. There is the informational dimension, that as you move up the ladder, you need more and more information. And of course, there is the reasoning dimension, that as you move up, then you have more sophisticated reasoning, association, intervention, and that counterfactual. The other important thing that's from today's interventional reasoning is not as refined as counterfactual reasoning. And we've seen examples of that. So it cannot unveil certain details or aspects of a situation. And the last thing I want to end up with is there's really two pillars of counterfactual reasoning when you think about it. This notion of functional relationships, causal mechanism, which allows you to see the blueprint of a situation that's needed, and this notion of being able to transfer information from one situation to another, which could possibly be conflicting. You're somewhere, you observe something, and what is it? What is it that I want to squeeze out from that experience and use it when I'm contemplating an imaginary situation that has information that conflicts with the first? There is something that is invariant to both of them. And I hope we also gave that dimension enough attention. All right, guys, thank you. I will stop here.